time for your 2015 free response questions video key. Number 1, we have rate at which rainwater flows into a drain pipe, and that is given by a function right here. And then we have water draining out of the pipe here at a rate of that right there. And we have 30 cubic feet of water in the pipe. So that's all the key information. Of course, make sure you read through the problem thoroughly, but I'm trying to shorten it up a little bit. Part A, how many cubic feet of rainwater flow into the pipe during the 8-hour time interval? So that is the integral of the rate at which water flows in. So from 0 to 8 of R of t dt. And you can just use math 9. And remember, you can actually write R of t like that. Even if they didn't name the function, you could name it whatever you want somewhere, define it to be R of t, and then write R of t rather than rewriting the whole function a bunch of times when you need to use it. But there is the answer right there. Okay, on B, is the amount of water in the pipe increasing or decreasing at t equals 3 hours? Excuse me. Give a reason for your answer. So if we need to compare R of 3 and D of 3, whichever one is greater, then we know if this is greater than if R of 3 is greater than D of 3, then there's more water going in, and vice versa. And so here are those values, and we can see D of 3 is actually greater, and therefore the amount of water in the pipe is decreasing at t equals 3. Part C, when do we have a minimum? So we need the amount of water in the pipe, and then find the minimum. So the amount of the water in the pipe between 0 and 8 would be, I guess I already have it written down here. I graphed these. I graphed the two different rates and saw when R of t was less than D of t, and after that when R of t was greater than D of t. Because if R of t is less than D of t right here, then the amount is decreasing. So we know it's decreasing there, and when it switches to this, then we know the amount is increasing, giving us a minimum at that time. So you can just look graphically when that happens. And then part D, the pipe can hold 50 cubic feet of water before overflowing. Water continues to flow into and out of the pipe at the given rates until the pipe begins to overflow. Write but do not solve an equation involving one or more integrals that gives the time W when the pipe will begin to overflow. So for that, we know that we want the amount that goes in. So for the integral from 0 to W, because they said time W of R of t dt, minus the integral from 0 to W of D of t dt, plus the initial amount 30, and we want to know when that equals 50. We actually want to know when it exceeds 50, but they said write an equation. And so there you go. On this key, I wrote it as a single integral. But remember, you can split up integrals like those two things, so they're being subtracted from one another. So that's no problem. Okay. Number 2, I've already found the intersection point here and jotted that down because we're going to need that for different parts of this question. But part A, find the sum of the areas of regions R and S. So what we have is this function right here is the quartic g of x, and then this function is our function f of x, and that's important because it switches at the intersection point that I labeled in green which function is above versus which is below. Because to find the area of a region, you do integral of the curve that's above minus the integral of the curve that's below. So we're going to do 0 to the intersection point of orange minus purple, so f minus g, g minus f, and then from the intersection point until x equals 2, we do f minus g. So here this is written down for you. Okay, and then you can calculate all that just using math 9. Part B, region S is the base of a solid whose cross-section is perpendicular to the x-axis are squares. Find the volume of the solid. So we're looking at region S. I guess I'll leave that there. So the length of a square is going to run from this curve to that curve. Okay, so again, we've seen problems like this a couple times now. Imagine that these squares are like coming up out of the iPad right at your face. So try to draw it in perspective here. Okay, these are like lifting up off the paper, and there's a bunch of them like right next to each other. And they all have different heights though, and that's how you form these different shapes. Find the volume of that solid. So remember, the volume of anything is the integral of the area of the base times its height. Our height would be this thickness right here, like the gap between those two things, or the amount of space between those two things, which we call dx. And so the length of the square, that first red line I drew, is just f minus g. So we do the integral of f of x minus g of x. So that's the side length of a square. Square it for the area, multiply it by its thickness for volume, dx, and we're going from our intersection point, 1.033 to 2. And I'm just rounding this bound when I write it, but I'm not rounding it when I do a calculation. Okay. So there you go for the answer. And then let's get rid of all that stuff. Part C, it says let h be the vertical distance between F and G and region S. So this is similar. It wants us to find the rate at which h changes with respect to x. So h is just this length right here. Okay, so that is simply the top curve, which was f of x minus g of x. So h equals f of x minus g of x. And therefore, h prime equals f prime of x minus g prime of x. And we just want to know when that's at 1.8. So you find f prime of 1.8, plug in 1.8 right there, plug in 1.8 right there, which you can just use Math 9 to do that. You don't actually have to find the derivative. And there you go. All right. Number 3. Johanna jogs along a straight line. All right, so we're given velocity and a data table. Use the data table to estimate the value of v prime of 16. We've seen a question like this. I think this is the third time they like this question. So to estimate v prime of 16, you find the slope between 12 and 20, which 16 lies between. So here's the work for that one. There you go. Notice the units are important. Using correct units, explain the meaning of the integral from 0 to 40 of the absolute value, and then approximate it using a Wright-Riemann sum of 4 subintervals. So integral of absolute value of velocity, we should know is total distance traveled from 0 to 40. And then the Wright-Riemann sum from 0 to 40 using 4 subintervals. So we're going to go here to here, a length of 12. Here to here is 8, then 4, then 16. And using a Wright-Riemann sum, we're going to use, this would be the right height for the first interval, this one, and then use this interval length, which is your base length, so 8 times 240, and then we're going to go 4 times negative 220, although that's going to be positive because we're doing absolute value for total distance traveled, and then 16 times 150. If you're having trouble still looking at or seeing that from a data table, then just plot all those points and actually draw the rectangles, and I think you'll see. But here is the work for that. Okay, kind of some big numbers without a calculator, but things you have to do nonetheless. Part C, Bob is riding a bike. He's got a velocity function. Find Bob's acceleration. So from a velocity function, acceleration is just the derivative with 5 plugged in. So there's the work for that. And then part D, based on the model B from part C. So for Bob, find Bob's average velocity. Average velocity is, since we're given a velocity function, and we're trying to find the average value of the velocity, it's integral divided by interval length. Okay, so here's the integral divided by the interval length. I found my antiderivative, plugged in 0 and 10, subtracted, and I have a 1/10 out in front because that's the interval length to give me the average value. Number 4, I'll let you guys construct the slope field, but you can check it here. There's what it should be. Part B says find the second derivative in terms of x and y. So the second derivative in terms of x and y, because we're going to have a y prime here, so we're not allowed to have a y prime. So our second derivative is 2 minus y prime, but this is y prime, so it's actually 2 minus 2x minus y, which is equal to 2 minus 2x plus y. So that's our second derivative. And it says determine the concavity of all solution curves for the given differential equation in quadrant 2. So if it's in quadrant 2, then we know x is negative and y is positive. So if x is negative, this will come out positive. This is already positive because it's a y in quadrant 2, and this is positive. So our second derivative is always positive. If our second derivative is always positive, then the function is always concave up. Okay, let's see. So here we go. In quadrant 2, y will always be concave up since y double prime is positive. You might want to go on and state a little more that in quadrant 2, well, I think that's probably good enough. But I kind of verbalized it before. I know in quadrant 2, this will be positive and that will be positive, so it's all positive. Part C, let f be a particular solution to the differential equation without an initial condition. Is there a min, max, or neither at x equals 2? So we can look at a sign chart for this. But first, if there is a min, max, or neither, then it needs to be a critical point. So let's test to see if this is a critical point, and you plug in 2. Remember, for a critical point, the derivative would have to be 0 or undefined. So if we plug in 2, 3 into our derivative right here, you get 4 minus 3 equals 1. But that's not 0, so you don't get a critical point, which is what I've said right here. So it has neither a max nor a min at 2, 3 because the derivative isn't 0. And then part D, find the values of the constants m and b for which y equals mx plus b is a solution to the differential equation. So most people probably recognize this question as something we did before, a long time ago. And I did say at the time that I saw it in another set of questions, so here it is. So let's go through this again. If y equals mx b is the solution to the differential equation, which is this, okay, if something's a solution to anything, that means if you plug it in, you get a true statement. So we can just substitute for our y up there, 2x minus, instead of y, we can say mx plus b. But if y equals mx plus b, then our dy dx is simply m. So now instead of this, I can say m. And now a little side note here, so this has nothing to do with this problem directly. I'm going to just make up some numbers. If I have two lines like 2y plus b, or not, sorry, 2x plus b equals negative mx minus 4 or something like that, just making up numbers. But if two lines are equal, then their slopes must be equal and their y-intercepts must be equal. So the slope of this line is 2, which means negative m must equal 2, which tells me then that m equals 2. And then similarly, we can conclude that b must equal negative 4. So you get b equals negative 4. Okay, so we're going to use that logic over here. Now this looks a little more confusing than that, but we can manipulate this a little bit. So we get 2x minus mx minus b. Okay, this m right here is a constant. I know it came from the slope of something, but it's still just some number. So that's actually the y-intercept of something. So let's move either one of these x terms to the other side, because every line is of the form y equals mx plus b, or it can be written that way. So let's just add mx to make things positive. So you get mx plus m equals 2x minus b. Now we have two lines that are equal to each other, so this slope must equal this slope. So now we know m equals 2. And Our y-intercepts, which are m and negative b, must also be equal. So we know m equals negative b, which means we know 2 equals negative b, so b equals negative 2. Okay. This is shown a somewhat different way. I'll explain it very quickly. Basically, I wrote this equation, same thing we had on the other sheet that I just explained. But if something's a solution, then it's always true. So this is true no matter what x values I choose. So I chose 2 random x values right here, and then plugged them in to this equation, and got this equation and this equation. And then what I've created there is a system of equations with just m's and b's. And so I took this m right here, substituted it for that negative b because they were the same, they were equal, and I solved the system. And either way, you get the same answer. So that's a different way to think about it. So you can do it that way if you want. Number 5, we have a graph of f prime. They tell us there are horizontal tangents at -1, 1, and 3, which is kind of what it looks like, but you would need to know for sure. And then this area is 9, and this area is 12, they tell us. Find all x coordinates at which f has a relative max. There is a maximum when the derivative changes from being above the x-axis to below, which is going to be at -2. Okay, so there's a relative max at -2 because that is where f prime changes from positive to negative. On what open intervals is the graph of f both concave down and decreasing? So if it's concave down and decreasing, so it's decreasing anywhere this is below the x-axis, so that's where f is decreasing. And remember, concave down, the definition of that is decreasing slope. But we're looking at a graph of slope. So we want to know where this function itself is decreasing, which is there to there and there to there. Okay. So -2 to -1 and 1 to 3, because that is where the function is both below the x-axis and decreasing. Below the x-axis tells us f is decreasing, and the f prime graph decreasing itself tells us f is concave down. All right. C, find the x-coordinates of all points of inflection for the graph of f. So inflection points are where f double prime equals 0 and changes signs, which are maxes and mins of the derivative graph. So it should be -1, 1, and 3, which I've said right there. And part D, given that f of 1 equals 3, write an expression for f of x that involves an integral. Find f of 4 and f of -2. So this is one of those very typical questions where we can do the integral of f prime. I'm going to use t in here and do my bounds from, I'm going to choose 1 up to x, okay? And this equals f of x. And the reason that I'm choosing 1 for my lower bound is because that's a given value. And then when I calculate f of any number, I just plug in whichever one I want for my x right here. And then I can, that's a calculatable area from the graph, and then one value will be unknown and one value will be known. So what I mean by that is, remember, the antiderivative of f prime is f. So if I do the integral now from 1 to 4, so evaluating f of 4, so this is equal to f of 4 of f prime of t dt. Oops. I get f of 4 minus f of 1. But the integral from 1 to 4 is this area, which is -12. So I get -12 equals f of 4, which I'm trying to find, minus f of 1, which is 3, and then you just add 3 to both sides, and you get f of 4 equals -9. Okay, and then you do the exact same thing here, just with different numbers in different areas to get f of -2. And finally, number 6. All right, so they give us an equation, and they show us what the derivative for that equation is. Write an equation for the line tangent to the curve at -1, 1. So we need the slope, so we're going to evaluate this at -1, 1, which will give us 1 over 3 plus 1, so 1/4. Okay, I'm just going to check that real quick with my already drawn out key. Okay, that is the correct slope. And then, so now you can do point slope using this point. So you do y minus 1 equals 1/4 times x plus 1. Okay, here's a cleaner version of that work, I suppose. Find the coordinates of all points on the curve at which the line tangent of the curve at that point is vertical. So remember, so this one's a little bit tricky in a sense. Hopefully you know that you're going to get a vertical tangent line when the derivative is undefined, which is going to be when the denominator is 0. So you do 3y squared minus x equals 0. Now typically we solve this for y, but if we solve this for y, we're going to end up with plus or minus square root of x. And then you got to plug that in for 2 different y's here. If you go through the algebra, you're going to see you're not going to be able to solve this equation without a calculator. So we actually solve this one for x. And you get x equals 3y squared. So now we can plug 3y squared in for x up here, and we get y cubed minus 3y squared for my x times y equals 2. And that's y cubed minus 3y cubed equals 2, which gives me negative 2y cubed equals 2, which gives me y cubed equals negative 1, so y equals negative 1. Okay, let me give you a cleaner version of that work right here. Okay, so there's a nice version. And then after I find y equals negative 1, I just plug that in to the curve. So now I know y equals negative 1. Let me get rid of all this other stuff here. So if y equals negative 1, I can just plug that in right here and get negative 1 plus 1 plus 1y equals 2. And so it looks like y is going to equal 3. Which is how I got that. Or sorry, x. I wrote y. I was solving for x here. I plugged in a number for y, so that would be an x. And finally, evaluate the second derivative at that point. So we just got to find the second derivative using quotient rule. Derivative of the top is y prime times the bottom, 3y squared minus x. Well, I'm out of room. Minus the derivative of the bottom, 6y y prime minus 1 times the top, all over the bottom squared. Okay, and then you just plug in negative 1 and 1 to that. I'll let you go through that arithmetic. But here it is, so you can check yourself. Make sure you can do these things without a calculator, because we do mess up arithmetic sometimes. All right, and that is it.